All right, sorry everybody. Too late here. I hope everyone's doing well. There's no video posted from Monday because I guess, I mean, I apologize for the short notice, but I guess no one was able to attend at 9 o'clock. So, there wasn't really anyone there for me to instruct or teach. So I didn't post anything from that call. But yeah, so we'll kind of do class and everything today and as well as on Friday. And so, yeah, and we'll wrap up kinetics these 2 days, but, again, but as I mentioned last week, right, videos of kind of things we'll go over today and stuff like that are also posted. But I wanted to, still do kind of these class periods for people to be able to ask questions and things like that. So I'll say, I've seen most everyone's faces and things like that. But I think in the future, especially next week when Kelly takes over, if you're able to turn on your webcams so she can kind of see people, get to know people, have a little bit more of an interaction besides just seeing a name on the screen, right? I think that'd be very useful and very helpful for her. So I encourage you to do that, at least starting next week. If you don't feel like doing it today, that's fine. I've seen all your faces and things like that, but yeah, just as kind of a future thing. So, all right, so let's get going. So are there questions anyone has? I know we didn't have our normal Monday class, so people couldn't tell me about what I did wrong on the weekly quizzes. Was there anything wrong people felt like I screwed up on the quizzes, or or maybe just have a question about answers or things like that? Anyone have anything related with that, or course material or otherwise? I posted grades for homework 1 online. I know I've gotten an email from some people who turned theirs in class to request a scanned version of their homework, and I promise I'll get that to you. So if anyone else who turned theirs in class and hasn't emailed me about it wants a scanned version of their homework, just shoot me an email and I can scan it for you. Yeah. I think that's kind of it for announcements. So if there are no questions from anybody about anything related to the course, whether it be that the weekly quiz last week, lecture stuff for this week, exam, or anything. When is the test again? So it's unchanging. Sorry, I accidentally, when I opened up the chat, shifted things on my screen and I accidentally paused the recording, stopped it. Yeah, no, the exam date didn't change. There's, I once set up in the syllabus the exam dates. I don't like changing those unless like everyone in the class is fine with it, basically. And there was enough people that said they did not want the date to change. And so I didn't want to change it because sometimes you have things going on a week. Maybe you had to make a doctor's appointment for next week, and so you're like, well, I can miss class on Monday, but I can't miss class on Friday, right? And things like that, right? So that's what I give the exam dates at the beginning of the year, so you can make sure you can attend those days, right? And so yeah, so there's enough people that said no, so that's not changing. But what's also not changing is what's on the exam. Okay, the quantum mechanics stuff is not covered on that exam. It's all going to be kinetics on this first exam, plus a little bit of kind of probability and math review things that we did at the beginning of the semester, right? Yeah, I had like a question or two on in the homework, right? The first like 3 or 4 questions, kind of probability math review type stuff. So that stuff is all going to be fair game for exam 1, right? But next week on Monday, you will start learning about quantum mechanics. Okay, and so yeah, so just keep that in mind. You'll have 2 lectures on quantum mechanics before your exam on kinetics, because of how we decide to kind of change things up a little bit to make it so, Kelly takes over a new kind of material, new set of subjects and things like that. So you have a more consistent kind of instruction for the different subjects. Okay. Any other questions? All right, well, again, feel free to ask anytime. Oh, did the homework due dates not change? No, because the exam didn't change, I didn't change the homework due dates. If the exam was going to change, then I would have made the homework due this Friday, but it's still a shortened homework. But I'd make sure to do those before the exam. So the homework is due again next week on Wednesday. So that hasn't changed from the original time because again, the exam didn't change. So, all right, let me start. Where is 9, right? Okay, yep. Let me start up the PowerPoint here, share that screen. All right. So talk about photochemistry, at least today. We'll see if we get to kind of polymerization, chain reactions, and things like that as well. But we'll first start off with photochemistry, okay? So you'll talk more, right? So today we're going to talk about the kinetics of photochemistry. Later on in the semester, you're going to learn more about the energetics, right? How light is absorbed in the molecule to change energy levels, how you have these discrete energy levels and things like that. And what are the selection rules and all this other wonderful stuff with spectroscopy, right? So you'll have a bunch of topics and lectures on spectroscopy and learn a lot more about that. But here we're just going to focus kind of on the kinetics. What happens in your system when you hit it with light in terms of what percent do you get in certain excited states, how long do they last in those different excited states until they decay down to the ground state or decay to some other state or things like that, right? So what happens kind of in terms of the dynamics that's involved with photochemistry, okay? Right, and the idea here, right, kind of in this image, right, is you have some molecule in some low energy state, you hit it with light, it goes to some higher energy state, right? And then the question is what happens, over time to that molecule in that high energy state, okay? Because that's a metastable state, right? That's not your stable state where it's going to stick in that higher energy forever, right? It's metastable. It will eventually go back down to the lower energy state somehow, okay? Right? So in this topic, I'll be using terms singlet and triplet electronic states, right? So, right, again, your electrons have discrete energy levels they can occupy, right? And again, you'll get a lot more discussion about that later on when you talk more about quantum mechanics, right? But there are certain, but when you have these electrons occupying these energy levels, that you can occupy what's called kind of singlet electronic states versus triple electronic states. And the difference between those has to do with the electronic spin, right? Right, the electron spin, right, which is that, m sub s type thing, right? Right, m sub s, right, is equal, right, if you remember this from general chemistry, right, you got m sub s. Why is that not doing this superscript and subscript? Right, equals, plus or minus 1/2, right? And that's related with kind of your electrons being spin up or spin down, right? And basically, when you have an even number of electrons and they're all paired up, you have even number of plus 1/2 spins, minus 1/2 spins. Often you represent these as arrows and things like that, arrow up, arrow down. When those are even, and paired up, right? You have, all electrons paired up in s and p orbitals, things like that, right? That's going to be a singlet electronic state because it's called singlet because there's one way to generate it. It's singly degenerate. Okay, most organic molecules are singlets. Okay, right. But if your electrons are not paired up and potentially occupy different orbitals, right? For example, oxygen molecule, when you'll get more to this when you do kind of MO theory and things like that, right? But the oxygen molecule, right? The highest energy electrons are in some p orbitals that are not fully filled up, right? You have kind of degenerate p orbitals, right? You know, so you have two orbitals, same energy, and then you can have an electron, you know, two electrons with the same kind of up spin, if you will, in those orbitals, right? And so the oxygen molecule is a triplet state in its lowest energy state because of this. Okay? And again, you'll get more into why is it form a triplet versus pairing up and forming a singlet and things like that, right? Why is it that you want to unpair electrons before pairing it, right? You kind of learned about Hund's rule and things like that, hopefully in general chemistry and how you occupy these orbitals and such. But again, we'll talk more about that. But the main idea, there's these singlet states, triplet states. Triplet states are triply degenerate, transitioning between them is very difficult unless you have heavy transition metals and things like that, like your actinides or lactanides. You know, these heavy atoms can induce this transition of singlet to triplet, and how it does that is it allows the electrons to flip their spin. Okay, you can't electron to flip its spin from plus to minus, plus 1/2 to minus 1/2, is not something that just does on its own on a very fast time scale. It's a very slow process. It takes a long time for it to do it kind of by itself, if you will. So, and so yeah. So why is that important? Right, the reason is most molecules are in the ground singlet state, and so when you excite them, you excite it into an excited singlet state, okay, and then they can decay into other things. So this slide has a lot of decays. We'll focus mainly on the ones that are kind of relevant to what we're talking about: fluorescence, intersystem crossing, phosphorescence, internal conversion, right? But there's a bunch of first order processes. These are all kind of first order. Well, I guess not really that bottom one, those bottom three, right? The first order processes, right, are all kind of these guys here, right? And then, you know, you have your second order stuff all kind of down here, right? If you will, right? And so, right, we'll focus on just kind of first order kinetics type things, right? Where you just have your molecule, it's been hit with light, right? That's the absorption, right? That primary absorption, that absorption, right, is when you get hit with light, it forms an excited state. The excited state is this S star, okay? So S stars is, you know, S for singlet ground state, right? S star for singlet excited state, right? So you form this excited state, right? And then the excited state can decay. It will go back down to the ground state. Not can decay, it will decay, right? And so, you know, the question is, how does it do it? Well, it could just re-emit light in fluorescence, right? So it could decay in that way. It could decay by doing internal conversion, right? Where it just directly goes back down to the ground state, and the energy that is given off in terms of vibrational energy and heat and things like that, right? And kinetic energy of your molecule and such. So, right, so internal conversion doesn't emit light. Instead, that energy goes into just increasing the vibrations and kinetic motion in your molecule, right? Fluorescence, you emit light, and that's where the energy goes off to, is in the form of light, okay? And then you have things like intersystem crossing, where your excited singlet state can form a triplet state, and phosphorescence, where that triplet state can decay, right? Now, in terms of speed of these processes, kind of as you go down this thing, you get slower and slower, okay? Right? So you get slower and slower as you go kind of down this list. Intersystem crossing is very fast. Typically, fluorescence is also very fast. Typically, and then internal conversion and phosphorescence for say organic molecules, right, is going to be a very slow process, right? This is why glow-in-the-dark materials, right, can glow in the dark for extended period of time, right? You have, glow-in-the-dark materials, right, where you have to kind of charge them, right? You hold them up to some light, and it absorbs a bunch of light. When it absorbs that light, it undergoes intersystem. Oh, shoot, I have these written wrong. In terms of the speed, problem is we should have intersystem crossing and internal conversion flipped. Those should be flipped, right? Internal conversion and fluorescence are very fast, and intersystem crossing and phosphorescent are very slow, right? So glow-in-the-dark materials undergo intersystem crossing, okay, to form triplet states. Those triplet states then live for a very long time until they can eventually phosphoresce, right, down to the ground state, right? Phosphorescence emits light and forms the ground state, right? And right, and that can take milliseconds, seconds, minutes, right? Phosphorescence is a much slower time scale than, say, fluorescence. Fluorescence is on the order of nanoseconds, picoseconds, even femtoseconds potentially, right? While phosphorescence and intersystem crossing can be on the orders of milliseconds, seconds, or minutes. Okay.
I had a question real quick.
Yeah.
So are these, I guess, events that you call them, are they specific to the compound itself, or are they specific to the state that it's excited to?
You mean like the events, whether or not they can occur, or the speed of the events?
I guess just which event specifically occurs. Like say, is it compound specific?
So which events occur? So all of these first order kind of kinetic events, okay, all of these can technically occur in any molecule. You excite any molecule into a single excited state, it can undergo any of these events. Now, the rate in which they occur depends on the molecule, right? So you might not get, for a lot of molecules, any triplet formation because this intersystem crossing is so slow compared to, say, the fluorescence or something like that, right? And so the rate in which they can occur depends on the molecule and depends on the state you excite into and things like that, okay? But whether or not they do occur is independent of the molecule. These all can occur for any molecule. Yeah. Now, some of these some of these second order processes, okay? So I guess, let's see here. How do I want to do this? Let me clear drawings here. So for second orders, these will always occur in any molecule they can occur. Now, exomer formation, this thing depends on your molecules that you're looking at. Okay. Or this kind of energy pooling event, this can kind of depend on the molecules and what are the relative energy levels in your molecules and things like that. So these might not all occur in every molecule. Okay, so not all of these will occur. These second order stuff in every molecule, but all the first order kind of events, up here, right? All of those will occur in every single molecule. And the rates are just dependent upon the molecule and the structure and electronic states and so on and so forth. Any other questions kind of about this stuff? Yeah. Let's actually talk about kinetics. So often we care about, what is the yield of a certain event, right? We've talked in this class, and you talk in different classes, right, about yields of products, right, in a chemical reaction, right? Well, we can think of this photochemistry as a chemical reaction, right? I have a reactant S star, and it's forming different products, right? S or T star or things like that, right? Or T star can form S, right? And so, right, I have effectively these chemical reactions, right? These photophysical reactions, right? You can think of as chemical reactions, right? And I can ask, what is the yield, right? I form S star and I have a bunch of different decay products. What is the yield for a specific type of decay, right? And so often that's referred to as like the quantum yield, okay? So the quantum yield of, say, fluorescence or something like that would be related with, say, the number of desired events. So if I'm looking at the quantum yield of fluorescence, right, I'd want to know how many molecules underwent fluorescence versus how many molecules, right, formed that excited state, right? So fluorescence occurs by getting into S star state, and then the S star state decays down to the S, the ground state by emitting light, right? And so the number of photons absorbed it tells me how many S star states, right? How many excited states did I form, right? And then the number of fluorescence events that I got out, right, is my number of desired events, right? And the ratio of that would give me my quantum yield, right? You can multiply it by 100 to get a percentage if you wanted, right? But that would be my quantum yield, okay? Well, the number of events that occur can just be related to the rate in which those events occur times some time scale in which they occurred over, right? And so that time scale for both kind of the absorption events and the emission events would be the same, okay? And so I can get this quantum yield by just looking at the rate on which the event I want occurs and divide that by the rate in which you're absorbing light. So I absorption is the rate of absorption, okay? It's just typically given I is the symbol that's used for that, so that's why I use it here. But I at ABS, right? I absorption is that rate of absorption, okay? And so the question is right, what is the rate of the event I'm caring about? So VI, right, is saying the rate of some process I, right? The rate of fluorescence, the rate of intersystem crossing, the rate of internal conversion, right? What are those rates? And can kind of simplify this expression here for this quantity, okay? And so to do that, we'll look at the fact that we have a bunch of first order kinetic reactions, right? They're all parallel to each other, right, and competing with each other, right? They all happen simultaneously, okay? They don't depend on the other to happen, okay? And for these three events, emission, internal conversion, and intersystem crossing, right, they all use the same reactant, S star, okay? And then this first event, right, the absorption is the formation of that S star, okay? So let's assume, right, there's no light being shined on your molecule. We've just formed a bunch of excited states, right? What is kind of, right, the kinetics of that excited state, okay? And so, assuming these are the only events I care about, right? I have some isolated molecules, so none of these second order events can occur, right? These are the only events I care about, right? So the rate of change of the concentration of that excited state is just related with the rate of these three reactions, right? Which is Kf S star, Kic S star, and Kisc S star. So I just add all those together, right, to get minus Kf plus Kic plus Kisc times concentration of S star, okay? And this is our first order, rate law, right? Which means we can just easily integrate this out to get the integrated rate law for first order reactions, okay? And so you do that, right? And you get your integrated rate law for first order reaction. And I'm going to rewrite that as this e to the minus t divided by tau naught, okay? Where tau naught is defined as the lifetime, okay? So tau naught is the lifetime of your excited state, okay? And it's given by 1 divided by the sum of these rate constants, okay? That's just by definition, okay? So by definition, tau naught is 1 over the sum of all kind of rate constants in this kinetics, the set of parallel first order kinetic problems, okay? Right, and so that's right. This is what the excited state will look like, right? So if you measure in the lab, using different spectroscopic techniques, right? What is the concentration of these excited molecules as a function of time? You'll see some type of exponential decay, right? Where the how quickly it decays is given by this tau naught, okay? And that's something that you can usually fit to and measure to get the lifetime of your molecule, right? So whenever you talk about the lifetime of some excited state, right, they're basically fitting the concentration of that excited state as a function of time to this equation, right? And backing out that tau naught, that lifetime, right, for the excited state. Okay. Questions about that? Questions about how we got this integrated rate law? Why the change of concentration of S star is just related to the sum of these rate constants times the concentration of S star? Oh, let's see something. Check here. Why is that not pulling up? There it is. All right. So just a note here from Kelly that I'll just kind of point out, make sure people see that in the chat. Okay. So she's going to make a survey on Canvas. Please participate. She'll give you credit for participating, but please participate and everything. So for that survey. Okay. And then, and as she mentioned, right, it's just mainly questions for her to kind of get to know people in the class and everything like that, right? So kind of, again, participate with that, right? You know, imagine, you know, next week's kind of her first day of class. She wants to get to know people, but we can't, you know, but you're not in person, right? You're all over Zoom. And so it's good to kind of help out participating in these things. Okay. All right. And so, right, so we have kind of what happens if we shine light on a molecule and just ask what are the kinetics of the excited state after I turn the light off, right? And that's just this, you know, first order integrated rate law, this exponential decay, right? So I can also look at what do the kinetics kind of look like if I continue to shine light, right? So if I have constant illumination, right, I'm going to have this rate of decay as we had before, right? All these different processes cause the decay of that excited state, right? The loss of the excited state. But then I also add on the rate of absorption, right? IABS, that's the rate of absorption by definition, okay? And so I have my rate of consumption, if you will, plus the rate of formation, right? The rate of formation has to be absorption. It comes consumption are these decay processes, okay? Well, if I have a constant illumination, right, I will reach a steady state situation where the concentration of S star is not changing over time, okay? And so that change concentration is 0, right? And so I will eventually reach a steady state concentration S star that kind of satisfies this equation, right? That the excited state concentration times the sum of these rate constants, right, will give me an overall rate of decay that's equal to the rate of formation that's given by the rate of absorption, okay? So this is just saying, right, that when you reach the steady state concentration of S star, right, the formation rate of S star is equal to the consumption rate. And so, right, and the consumption rate is given by the concentration of S star times these rate constants, and the formation rate is just given by the I absorption, this rate of formation, okay? And so now I have this absorption rate related with my rate constants and my concentration of S star, okay? So I can plug that into this quantum yield definition, okay? And notice the fact that, let's say I'm looking at fluorescence, right? The rate of fluorescence is just Kf times S star. Well, the rate of absorption under the steady state conditions is given by Kf plus KIC plus KISC times S star. So these S star concentrations cancel out, and we're left with this final fluorescence yield, okay? So the fluorescence yield is just defined as Kf over the sum of all of the rate constants. And if you remember, when we started talking about kinetics, we did a situation where we had parallel competing first order reactions of the decay of acetic acid, right? And one of the products was a ketone. And we asked, right, what is the quantum yield for that ketone? The quantum yield ended up just being, right, or we didn't say quantum yield, right, but what is the yield of that ketone, right? The yield was just, right, the rate constant for the ketone reaction divided by the sum of all of the rate constants. And you get that same thing here in photochemistry, okay? Because we have a bunch of first order competing parallel reactions, right? The yield of any specific reaction is just the rate constant of that reaction divided by the sum of all the rate constants for all other possible reactions. Okay. And so, right, if I want to know what is the yield of intersystem crossing, it would be KISC divided by the sum of KF plus KIC plus KISC, right? And so it's just that very simple formula to get the yield for fluorescence, for internal conversion, for intersystem crossing, right? Questions about how we got this? All right. So, right, going back to what we were talking about a little bit earlier, right? We have a molecule absorb some light. In general, the question is which of these processes has the slowest rate of decay? Stimulated emission, phosphorescence, internal conversion, and fluorescence. Yeah, so a bunch of people saying B, yeah, B, phosphorescence, okay? So internal conversion and fluorescence, as I mentioned, right, are very fast and typically similar time scales depending on the molecule, right? But picoseconds, nanoseconds, femtoseconds type thing. Stimulated emission is similar. I didn't focus too much on that, but stimulated emission is very fast as well, okay? But phosphorescence, right, involves this transition from triplet to singlet state, which is very slow for most molecules, okay? And then, so often phosphorescence is gonna be the slowest kind of rate of decay of all of these things, okay? All right, right? So let's say I have some phosphorescent crystal that I illuminated with some light, right? At time 0, the light beam is turned off, right? So I've illuminated this, I formed some initial concentration of excited states, and then I turn off the light. And you measure then the intensity of the phosphorescent radiation, right? The intensity of light that's emitted over time. And then the question is, what is the equation that best describes that phosphorescence intensity as a function of time? Is it that the intensity of the phosphorescence is constant over time? That it decays linearly with time? That has this logarithm dependence? Right? Or again, kind of a linear decay, but instead there's this natural log dependency in here. Okay. All right, yeah, I got some C's from people. Yes, it is C. So, right, this phosphorescence process, right? Let me go back here, right? Oh, I guess it's not written on that slide. Why does it take me so long to go back, right? Phosphorescence, right, is a first order process, okay? Right, this formation of light, right? You're measuring the intensity of the light that's being formed, right? Which is giving you, right? The intensity of light, as you'll get more into as you talk about quantum mechanics, is related with sort of the concentration, how much light, okay? As you increase the intensity, you're increasing the number of light particles, number of photons, okay? All this fun, wonderful stuff you talk about in quantum mechanics. Which is super cool, super exciting. You know, I think hopefully a lot of you find it very interesting. I always find it just fun stuff to talk about. Okay? But anyways, right, so this intensity of light gives you how much light is being formed, okay? How many light particles, how many photons, okay? So that's really that concentration, right? And it's just a first order kinetics problem. So it should have this first order integrated relate law dependence, right? Which is the natural log of that intensity, right? That concentration is related with temperature, right? Or time, right? So you have this natural log dependence or exponential dependence, right? If you were to write it out, right, this would be kind of exponential, or you know, the intensity is equal to the initial intensity times exponential minus KT, right? And so you should expect that you make that plot C will be the appropriate plot or appropriate line to fit for that intensity as a function of time in this measurement. Okay? And again, just because it's a first order kinetics event. Okay. All right. So a very important aspect of photochemistry is a process called quenching. Okay. So quenching is a process that occurs where you have some molecule that's photoexcited and another molecule comes on by, maybe it collides with it, doesn't even need to collide, just to be near it. Okay. And it can take the energy away from that excited molecule and bring it back down to the ground state, and then this new molecule will become excited. Okay. That new molecule is called the quencher because, right, it quenches the excited state. Right, you can imagine, right, your molecule that's excited, it has a flame. Right, it's hot. There's a flame on it. Right, it's burning. Okay, this quencher comes along and quenches that flame, gets rid of all that energy. Right, and takes it for itself. Right. And so that's, so that's why it's called a quencher, because it quenches that energy, it takes that energy away from the molecule you're interested in. Okay. And so the kind of kinetics of that reaction is given here, right? That you have some excited state on your molecule you're caring about, right? The singlet excited state, it interacts with this quencher and it forms the ground state of a molecule, right? So this is another way to get the ground state from excited states. Okay. And so when we do that, the rate of that process is just given by the quenching rate constant times the concentration of the quencher times concentration of your excited state. Okay. Now I'll note here, I worked out on detail in other slides that are posted online, right, in YouTube and such, how we get these Stern-Volmer equations down here. But I'll just note one of the assumptions, and it's not really an assumption, but one of the things that you use is the fact that this concentration of your quencher isn't changing based off of this reaction, right? This reaction isn't causing the quencher to do something, okay? So the concentration of your quencher is constant over time, right? And so the concentration of your quencher is really just a constant, okay? And so this KQ times Q concentration, right, is just some net rate constant K, right, times S, which again is just a first order rate equation. Okay, so if Q is constant, this equation just becomes first order, right, total, because it's just dependent upon the concentration of S star. So it's a first order process, and when you do that, okay, that will affect the lifetime and yields and things like that, and you can basically get a equation that relates the change in, say, fluorescence yield or change in your lifetime that depends on this concentration of your quencher. Okay. So for example, the first equation is saying that the intensity of your fluorescence, or that fluorescence yield without the quencher divided by the fluorescence yield with the quencher, just ends up equaling 1 plus tau naught, the lifetime without any quencher, times KQ, that quenching rate constant, times Q. Okay. Well, in lab, what you can do is you can just take your molecule on its own and measure its lifetime. That will give you tau naught. So I can measure tau naught on its own, and then I can do an experiment where I vary the concentration of my quencher, and I measure what the fluorescence yield is versus concentration of my quencher, and then I can make a plot given that data, and that will give me what this quenching rate constant is, KQ. Okay. And why does this matter? Well, often we care about the rate constant of this quenching, okay, because we can use that to study other aspects of chemistry, okay. This type of process, the Stern-Volmer plots and with quenching and things like that, has been used numerous times to study distances in solutions, dealing with polymers or other things like that, where it may not be easy to measure the distance in some other way, but the rate of this quenching constant often depends on the distance between your molecule and the quencher, and so you can back out that distance by doing certain measurements and things like that. So it's very cool stuff and very useful type of chemistry. Okay, but it's all related with kind of just the simple kinetics. Okay, the fact that concentration quencher is unchanging, so this ends up being just kind of a first order kinetics rate that's added on to the other kinetic processes that can occur, and that affects, say, the lifetime of your molecule by this form here, or the fluorescence yield by this form up here, which again is really the kind of these Stern-Volmer equations, as they're called. Okay. Questions about quenching?
I was just wondering if Q is like basically, I guess I was wondering what happens to Q. Does it not get into an excited state as well if it's quenching that excited state of S?
It does, but the idea in these experiments is typically that quencher then quickly gets rid of that excited state at super fast time scales, right? So technically, you are kind of using up your quencher and forming an excited state in it that maybe then it in its excited state can't quench another molecule, but you pick these quenchers and things like that because they quickly immediately get rid of that energy in potentially femtosecond time scales. Okay.
So the rate's just so large that you essentially assume that concentration of Q is constant.
Yeah. That essentially, right? Once you form the excited state quencher, it's immediately consumed. If you immediately goes back down to the ground state. So the net concentration, it looks effectively unchanged as you're measuring things over time.
Okay.
Yeah. Other questions? All right. So let's say, let's consider the quenching of an organic fluorescent species that has a native lifetime without any quencher of 6 nanoseconds. Sorry, there's molecules being quenched by some transition metal ion, okay? And there's a quenching rate constant, 3 × 10⁸ liters per mole per second. And the question is, what is the concentration of the quencher required to decrease the fluorescence yield of our organic species to 50% of its unquenched value? So this is a little bit of a more involved multiple choice question here. So I'll wait just a minute for people to attempt to kind of work this out on their own, and then we'll kind of do it together. All right. Anyone? Anything? I don't know when these were submitted here. Okay, so some C's. Just looking at the time of the people. So we got some people saying C, right? So yeah. So how do we get this? Right. C is the correct answer, by the way. It is C.56 moles per liter. And how do you get that? Right. Well, it's basically right. Use the fact that I'll go to the actual equation here, right? That this fluorescence yield without the quencher divided by the fluorescence yield with the quencher is equal to 1 plus tau naught KQ times concentration of Q, right? So we have that Stern-Volmer equation, okay? And then the fact is we were told that, right, we want the fluorescence yield to be 50% or 0.5 the initial fluorescence yield. We're given the lifetime in nanoseconds. I'm going to convert that to seconds. I think it's 6 times 10 to the minus 9 seconds, if I recall. I believe so. And then KQ we're given in terms of inverse molarity, inverse seconds. Okay. And so it's really just plugging in here, right? So it's plugging in P equals 0.5 P naught. Okay. To get on this left-hand side, you'll get 1 divided by 0.5. Okay. Right, this will be 1 divided by 0.5. Okay. And then on the right-hand side, you have 1 plus, then, you know, your tau times your KQ times Q, right? And so then it's just solving for Q, okay? And when you solve for Q, right, you'll end up getting C here, 0.56 moles per liter. Now, you might get like, you know, times 10 to the 7 moles per liter if you didn't convert this lifetime from nanoseconds to seconds. Okay, because the rate constant itself is in seconds, so you need to make sure your lifetime is also in seconds, or you need to make sure your rate constant's in nanoseconds, right? Which to convert this to nanoseconds, you divide this by 10 to the 9 to get this into nanoseconds, right? But right, and so when you do all that, again, your answer you'll get will be C. Questions about that? How to work that out? Right. The main trick here, right, is identifying, right, that this is what the problem is telling us, that fluorescence yield needs to be 0.5, the initial value. And then after that, right, it's just, okay, we got to use the Stern-Volmer equation. And I just got to plug in everything and make sure my units work out. Okay. All right. So here we have some molecules by pyridine, okay, that forms a complex with ruthenium, okay. This complex, so ruthenium bound with bipyridine, okay, can be quenched by the addition of iron, was that aqua iron or something like that? I always forget the name of like these water complexes, right? But an iron ion, basically iron 3 plus in water, right? And so that quenches it. And the question is given the following data, what is that quenching rate constant for this reaction? Okay. And what we're given here is the concentration of iron versus the lifetime of your bipyridine ruthenium complex. Okay. So for example, at time or at concentration of 0 of the iron, you have the lifetime of 60 microseconds. Okay. So how would I try to get from this data the quenching rate constant? What would I want to do? How would you kind of relate these things, right? Or what type of plot might you make? if you were trying to get that quenching rate constant.
Was it using the alternate Stern-Volmer equation?
Yeah, right. If you were to use that alternate form of the Stern-Volmer equation, right? What would you plot then with that alternate form? What would you want to plot in order to get that quenching rate constant?
1 over tau versus Q.
Yep, exactly, right? So let's go back to that form, right? Just so we can kind of see it, right? Right, so if we were given the lifetime, you know, and versus concentration data, right? So if I take 1 over that lifetime and plot it versus Q, right, I'll get a straight line. 1 over the lifetime is Y, Q is X, M, my slope, will give me KQ, and then Y, my intercept, will just be 1 over tau naught, right? And so, right, and so we do that, right? So I would, you know, put in Excel, right, the concentration of my quencher, and then 1 over the lifetime here in microseconds, okay? Right, and then you would plot this, and you'd, you know, fit it to a straight line, find the slope and things like that. Right here, you know, I'm not using Excel, so I just manually calculated the slope between 2 points and assumed it was a perfect straight line, right? You know, if you weren't fitting this, right, and whatnot, then what you'd want to do is you'd want to find the slope between all points and average them out to get the average slope, right? But here I'm just going to assume that the data gets a perfect straight line, right? But that obviously, again, isn't necessarily the case. And so to get that right, I get the slope by taking the y values, dividing by the change in y over the change in x, right? That's the slope by definition, right? And so I took these last 2 points here, okay? And when you do that, you get 0.0028 inverse millimolar inverse microseconds, okay? And that's the slope, so that is the rate constant, okay? Right, and you can convert that to molars per seconds or molar per picoseconds or how, you know, you can mess around with the millimolar and microseconds to whatever you want, but you don't need to, right? In this problem, those are the units given, so you're welcome to just leave it as that, right? But yeah, but you know, from this type of, you know, data, right, from doing these experiments, it's very easy to back out some of these rate constants, things like that, right, by just taking some simple plots like this and fitting some lines, okay? So any questions about this example? Any questions about photochemistry? I think what we'll do next is we're going to move on to talking a little bit more about polymerization reactions and things like that. But before we do, I just want to make sure there are any other questions about photochemistry, kind of what we talked about here, right? These competing rates, quantum yields, lifetime definitions, quenching experiments.
I have a question.
Oh, yeah.
So on the, I guess it's the phi equation, the rate of desired events, delta T and over rate of absorption. I think I might have just missed the bottom of that fraction in the center, the I ABS. Yes.
Yeah.
Is that'll be given, or is that something that we calculate?
No, so that is the rate of absorption. That's like VABS. That's the rate of absorption, and that's just some rate. You know, it would be something given, or you know, whatever. Like, yeah, you don't need to. That's not something you know or whatever. I just use this IABS because that's a common way to write the rate of absorption.
Okay.
But it's just a rate, right? It's like in these rate laws, right? VABS, right here in this next line, right? The rate of absorption is just defined as IABS. There's this absorption rate, right? Okay. And so yeah, right. And so that's kind of the rate law, if you will. Or, I mean, that's not really the rate law, but that's what it is, right? You could write out the rate law, some like rate constant of absorption times concentration of S times concentration of light particles and things like that. But
Thank you.
any other questions about anything here on photochemistry? All right, so let me flip over then to the other slide here. Talk about polymerization reactions. Okay. So we'll talk about some of this stuff, go over some of this. Okay. Why is it not clicking? There we go. Right. So there's two main types of polymerization reactions. I mean, there's further ones, but two of the major types of original polymerization reactions that would occur would be stepwise polymerization and chain polymerization. Okay. Here we'll talk about stepwise. Chain's a little bit more complicated, so we'll just focus on kind of stepwise polymerization. Okay. But right, polymerization is a reaction that's a chain reaction, right? Where you start off with a bunch of just small molecules, and they undergo some sort of chain reaction to continue to react and react and react with each other to bind with each other to form larger and larger molecules, right? That we call polymers, right? So again, these polymerization reactions are polymer forming reactions. Okay? Right, and so for stepwise polymerization, the main idea here is that any like of the monomers or polymers can link up with each other at any time. It's not that you have like just one thing that can react with other things and then it just keeps on reacting to form a longer and longer chain, right? It's that every molecule, every polymer is a reactant, okay? Right, in this picture here, the green molecules are the monomers, if you will, right? The purple are then the polymers that are formed, right? And so you can have multiple polymers forming at once, right? And the polymer can react with the monomer to form a longer chained polymer, right? And while not shown here, right, but these polymers can also react with each other, right? So on this bottom slide, right, I could have the end of this polymer react with the end of that polymer to form an even longer polymer chain, right? And so, yeah, so these polymers, right, can react with each other. They can react with other monomers, and monomers can react with monomers to form, smaller polymers, right? But everything can react with each other basically in this kind of stepwise polymerization reaction. Okay. An example of this is the form of nylon 66. So nylon 66 is formed by these stepwise polymerization reactions, especially formed by a condensation reaction, right? Where you have an NH2 group on one end of the molecule and a COOH group on another react with each other to form water, right? And then it forms a carbon-nitrogen bond, right? So you get some type of carbon-nitrogen bond forming, right? Formation, right? And form out in water, right? I mean, this is the type of reaction that forms proteins, right? From amino acids and things like that. It's these type of condensation reactions and such, right? But notice, right, that when you form kind of your polymer, now here my polymer consists of just two monomers, two molecules, right? But my polymer still has the reactive end, right? It has this NH2 end. Here I highlight the fact that this hydrogen, one hydrogen connected to nitrogen can break off and react with the OH group on the COOH end, right? Okay, and so yeah, so right, so I still have a reactive, NH2 end and a reactive COOH end on my polymer that can react with other monomers or other polymers, right? So again, right, that the idea of these stepwise polymerization reactions is everything in the solution, it can react with anything else effectively, right? Okay. Now, in this reaction, right, right, if I call a monomer A, right, this monomer A reacts with another monomer A to form this polymer A2, right, A subscript 2, if you will. Now, the number of reactive species has decreased through this reaction, but it's decreased by 1, right? Because again, each polymer is a reactive species. So if I have a polymer of length 100 monomers, right? So I've linked together 100 of these monomers to form a polymer. It is considered just one reactive species, right? Even though it's got 100 monomers, right? It's only got, you know, one end, right? You know, it's just got an end to it, you know, two ends, and those ends can react, right? Just like any monomer could react, right? And so every polymer is as reactive and can react with as many things as a monomer can, okay? And so the rate law for this type of reaction, right, is just given by the rate constant times the concentration of the monomer squared, right? Because it requires the monomer to react with the monomer, okay? Right? And so the integration of this would just give us kind of this second order integrated rate law that would tell us what is the concentration of our monomers as a function of time, okay? Right, and so this is just your typical second order integrated rate law, right? Okay. Right, but the question we want to ask ourselves, right, when we care about polymerization, right, we don't care about just how many monomers have I reacted, right? We care about how long of a polymer chain have I formed, right? That's what we care about. You know, and so to do that, right, we define the fraction of monomers that have reacted after some time as the initial concentration minus the current concentration, right, divided by the initial, right? Because that gives you, right, the initial concentration minus the current gives you how many monomers have reacted, right? Because the current concentration, right, again, initial minus current means how many have you lost, right? So how many have you reacted is how many monomers have you lost? And then we divide that by the initial concentration, okay? And so then just plugging in for this, you know, integrated rate law for what is the concentration as a function of time, right? We get this fraction of polymerization as a function of time here, right? Being KRT divided by the initial concentration of monomers divided by 1 plus KRT times the initial concentration of monomers, okay? And that's this fraction of monomers that have reacted as a function of time, okay? But what we care about is what is the average chain length, right? And, you know, or the degree of polymerization, right? So this is called the degree of polymerization, the average chain length, right? And so if two monomers, as I mentioned, right, you react two monomers together, you still get a reactive molecule, okay? So you've only lost one, right? No matter whether or not you have two monomers reacting, a monomer with a polymer, or two polymers reacting, the number of reactive molecules, right, decreases by 1 every time, okay? Right? And so, right, so if we think about like what is the number of reactive molecules that I have left, right, that changes based off of the number of monomers that have reacted, sorry, right, and to get the average polymer length, okay, that's just going to be related with how many monomers did I start with versus how many reactive sites do I have left, okay? So I'm going to consider, right, so even a polymer is again considered a reactive site, and so A here, right, is kind of my number of reactive sites I have left, okay, because again, a polymer can be thought of as just a monomer in terms of these chemical reactions, right? Again, the key with these stepwise chemical reactions is there's no distinction between a monomer, just a single molecule, and some polymer that's composed of N or N plus 1 monomers, right? There's no distinction between those for our reaction. So they all count kind of as the same thing. So this A really isn't the number of monomers, but more the number of reactive sites, okay? And so the average polymer length is the total number of initial reactive sites divided by the current concentration of reactive sites, okay? And, right, and here, let's just go to the next slide to see what that looks like, right? So if you were to plug in for the concentration of the number of monomers or number of reactive sites as a function of time, okay, using that integrated rate law, you just get concentration of N here, right, versus time, okay? Right, and you see that, you know, the average chain length, it has a kind of a linear increase in time, okay? But, and that's nice, right? But what we are curious about is, right, what is that chain length based off of how many molecules have I reacted, right? How many monomers have I reacted, okay? Because, you know, I can measure that in the lab, right? I can monitor the number of monomers using spectroscopic techniques and things like that, right? And I can use that, and I can potentially use that to then determine when do I want to stop this reaction from occurring, right? And so here we have a plot of this fraction of condensed, right? So the fraction condensed is the fraction of molecules that have reacted, right, versus the polymer chain length, right? And you see that the polymer chain length, right, even when I get to like 60, 80% of the molecules reacted is very small, right? Chain length is like N molecules or something like that, right? You know, or 5 molecules or something out of, you know, say 25, right? Right, that this number, that's the average chain length is still very small, even when you get like up to like 80% of your monomers reacting. Okay, and the reason is because again, this stepwise polymerization, right? Most of the initial reactions are going to be monomer reactions that are forming thin polymers of chain length 2, right? And so your average chain length isn't really increasing significantly, because really what you're doing initially is you're just forming a lot of very small polymers, right? And it's only when you get to having a small fraction of reactive species do you get this large, increase, okay, as the fraction of monomers that have condensed decreases, okay, from kind of this 80% to say 100%, right, or even 90 to 100, right? And what's happening here, why the chain length increases so dramatically with such a small change in fraction of polymerization, is because what's happening at this later time is that you're now reacting polymers with polymers, right? So now I have a polymer of length 10 reacting with another polymer of length 10 to get me a polymer of length 20, right? And that polymer of length 20 reacts with another polymer of length 20 to get me a polymer of length 40, right? And then 40 goes 80, 160, right? And so these things double in size, if you will, right? Theoretically, again, it doesn't necessarily automatically double in size every reaction, right? But double in size as you're starting to react polymers with polymers, okay? And so that's how you get kind of this functional dependence here of the average polymerization length of your polymer versus the fraction of molecules that have reacted, right? This condensed fraction. So questions about this stepwise polymerization? I lost track of time here. Okay, we got about 10 minutes left of class. Okay. Out of here, the main kind of concepts and ideas is just, again, to understand what is stepwise polymerization, how does it work, right? And then, the fact that it's a second order rate, follows second order kinetics, right? And then, how does that then relate to then this average chain length, right? Average polymerization length as a function of time, as a function of fraction of condensed molecules, or a fraction of reacted monomers, right? See here, the chat open somewhere. No, it's not popping up. There it is. Oh, just making sure here. All right. So that is kind of it for the new kinetics topics. So what I have here is a couple of examples related with just reaction mechanisms and solving for them using steady state and pre-equilibrium. So we can kind of talk about that. But right, that's mainly it, right? So the new kind of kinetic topics for this week were just photochemistry and these polymerization reactions. Okay, right? Because last week we finished up talking about unimolecular reactions and those type of kinetics, right? Again, there are videos posted talking about that are recorded and things like that, talking about enzyme kinetics. So if you're interested in that, you're welcome to watch those videos. You're welcome to shoot me an email asking me about them. I can, can discuss them with you, right? But those videos relate with like Michelson-Menten plots and experiments and things like that. And again, this enzyme kinetics are related with the rate of these things, is the concentration of substrates or enzymes and other such things. Okay. But yeah. Any questions about any of this stuff? Anything on kinetics? So Friday we'll just review for the exam. Okay. So I mean, we're at like a couple of minutes left. If there are no questions, I'll at least kind of discuss, some of these, right? I would highly suggest, we don't have the time to go over it today, but I did do some of these examples on videos online, and as well as solutions are kind of posted here, right, on the slides, right? But I recommend going over these examples, right? Just like going over the homework, to get extra practice with doing, say, these steady state approximations and, say, pre-equilibrium approximations. Okay. And so, right, what does the steady state approximation tell me or do for this mechanism? What is it saying, the steady state approximation?
That di dt is 0?
Yeah, that the change in concentration of your intermediate, which your intermediate happens to be labeled I, right, is equal to 0, right? So, right, di dt equals 0 is that steady state approximation, okay? Right, the rate of this overall reaction, right? Remember, again, the rate of the overall reaction is related with the rate of formation of products or the rate of consumption of reactants divided by their stoichiometric coefficients. So here, right, you can pick anything you want, any product, any reactant to rate the rate of reaction. I pick C here because C only appears in the second reaction, okay? So I can define, without any approximations being made, the rate of the reaction as dC dt, and that is related with Kc times concentration of I times concentration of A, right? So I can write this out without any approximation as my rate law for this reaction. But the problem is this rate law has an intermediate in it, right? And so we got to use things like the steady state approximation to get rid of it, which, as mentioned, right, the steady state approximation says di dt equals 0. Okay. And so how many terms is going to be that in that di dt expression?
3.
Yeah, there's going to be 3 terms, right? I'm going to have one positive term from the formation of I in the forward direction of this equilibrium reaction. Then I'll have 2 negative terms from the consumption of I in the reverse direction and the consumption of I in the forward direction in the second reaction, right? So I have 3 terms here. 2 of them are negative, 1's positive, right? And again, it's minus the rate of the second reaction, minus the rate of the reverse equilibrium reaction, and plus the rate of the forward equilibrium reaction. And then you can write out, right, what those rates are equal to in terms of their rate laws, because these are elementary reactions, right? And then I can just use that to solve for my concentration of I in terms of concentrations of reactants and products and rate constants, okay? And then I can just plug that in to my definition of the rate law, right? Plug in I into that definition to get the final expression here for the rate law, Kc, Kd times concentration of A squared times concentration of B divided by Kc, concentration of A plus Kd, K minus D, concentration of D. Okay.
So does the steady state approximation hold the best whenever, like in this example, like when Kc is much larger than Kd, like it's like as soon as that intermediate is formed, it's like immediately reacted? Like
yeah. So if Kc is much greater than Kd, right? Then what you would get here is this denominator would simplify to where if Kc was much greater than Kd, right? Then Kc times A would be much greater than K minus D times D, right? And so this denominator, this bottom term here, right? Let me get different color. Right? We can consider this kind of going away and just effectively being 0, right? And then rate law would simplify down to just KD concentration of A times concentration of B, right? Would be kind of the rate law that you would get, you know, if the second reaction Kc was very, very fast. And then you'd end up, you know, if the second reaction is very, very slow, right, compared to this above reaction, then you'll end up getting the pre-equilibrium approximation, which we'll see what that is, right? But that's when this term is effectively irrelevant, and I'm just with K minus d, right? And then I have Kc, Kd divided by K minus d times concentration of A squared times B divided by D, right? And that's what we'll get from the pre-equilibrium approximation, right? And you can get that from the steady state approximation by making the assumption that the second reaction is significantly slower than the equilibrium reaction, right? And then in general, if these are similar rates, right, then you would have this overall rate law, right? So this rate law is, you know, valid in a lot more instances than, say, the pre-equilibrium approximation will be.
And so are we assuming that the forward rate constant, or the rate for the forward reaction on the top reaction is greater than that of the reverse?
Not necessarily. So here we made no assumptions about any of those things. So with the steady state approximation, you're kind of assuming the concentration of your intermediate is constant as your reaction is going, okay? Which does, right, making that assumption means, right, that these rates have to be related to each other in this way, right? That the rate of formation of your intermediate has to equal the rates of consumption of your intermediate, right? That's what the steady state approximation is saying, is that the rate of formation of your intermediate has to be basically equal to the rate of consumption, right? So that's saying the rate of the forward reaction should if the steady state approximation is valid, the rate of the forward reaction should roughly equal the rate of the reverse reaction plus the rate of the forward reaction for the second reaction is kind of what it's saying, right? That's kind of the approximation that's being made, okay? And in general, that is a more valid approximation. And you don't have to have that. It could also be that the second rate is so much faster than the other ones that this approximation will end up holding true as well when you do kind of some math and things like that and show it. So yeah, it's the steady state approximation doesn't necessarily make an assumption about speeds of certain reactions. It sort of kind of does, but like in terms of this one's fast, this one's slow, no. It's more about how do the rates of the reactions relate with each other, but not necessarily which one's faster and which one's slower. That's only done with this pre-equilibrium approximation and the rate determining step. Yeah. So just right again, that pre-equilibrium approximation, you assume that the second rate is slow, first rate is fast and reaches equilibrium, which means that forward and reverse rate and the equilibrium reaction are equal. Use that to find that concentration of intermediate is Kd, concentration A times B divided by K minus D times D. Okay, you plug that in to get this final rate law expression. Okay, which again, you compare the steady state to pre-equilibrium, right? It is just basically using the steady state, you make this assumption and you'll get the pre-equilibrium approximation, okay? Right. But yeah, and so those are your rate laws using those two approximations, okay? But we're out of time for today. I'm happy to answer any other questions that people have, but I think we'll stop it here. Again, there is another example here of a lovely mechanism that you can go through and eventually, if you want to solve for the final rate law, here. Okay. So yeah. You can go through that and kind of work that out on yourself if you want to. It's going to be more complicated than most things you're going to see, right? So it's definitely decent practice, right? And then you can always check based off of kind of what I got on the slides here. Okay. Yeah. Any other questions before I end the session? Doesn't seem like, so I will end it here and we'll see you guys on Friday.